So, hello everyone, my name is Stefano Alberico. Thank you for the introduction. So let's say, like he said, we will move maybe from ground to space. I'll try to give you a bit an overview of what we have been doing with the company Scudo, my company, and basically we have done, let's say, try to do very practical application of cryptography. And of course, there is always this compromise that you have to be, you know, when you want to build a product and sell a product, they've seen probably very well, you have to, you know, compromise the level of, let's say, complexity that you try to build in your solution and try to keep the things, you know, working properly, let's say. But I will give just very, very quick intro about why, you know, we are doing what we are doing, and the kind of value as a company, why we end up doing this kind of product, and then try to focus really quickly on evolving satellite. So the company, okay, we are based in Estonia, and working with cryptography, actually we choose to work with the hardware-based cryptography. So which means, you know, like mentioned before, there are different kind of algorithms, and you can make an implementation, for example, using a software running on, you know, Raspberry Pi or any kind of CPU. Our decision was actually to go, let's say, all in into hardware, meaning using FPGA processor. I don't know, how many of you never heard about FPGA? If they don't know what is an FPGA, or how many know? Okay, so some, let's say, don't know. Let's say, when you want to implement an algorithm, whatever it is now, we talk about cryptography, of course, like I say, you can do a software, so, you know, build a program that then it's run by a certain CPU, you know, by a computer, which is usually quite complex, as an operating system, and which means as a potentially could be attacked by different direction. Or then there is one way also is to implement directly and run directly on a chip. So it's a physical integrated, you know, device that it's actually populating any kind of phone or laptop. So you have this little small physical device which can actually implement and run certain whatever algorithm you want. So in this case, you can get rid of completely, for example, of operating systems. So you can reduce the amount of software that runs and thus try to build a solution which is inherently safer. So what, in terms what you say, we reduce the surface attack. So you try to reduce the possibility to hack into a system. So we went into this hardware direction. And with this, we were a few years back, we were working with the European Space Agency Business Incubator in Estonia, the ESA-BIC, and through ESA-BIC we got some contract with the European Space Agency, which is a way of, let's say, I would say the first step, or when you want to build a product for space and you want to try, you know, to test it in space. So ESA is a nice, ESA in ESA contract is actually a nice, convenient way to get into space in a more affordable way, because space is quite expensive if you want to build your own satellite and build your own software and launch it. And so the other thing is, overall, we apply this hardware encryption to protect data communication in general. Then the application, as I say, mostly has been in space. But then, you know, cryptography doesn't really care if it is for let's say, securing your ID or make an election, or communicating with a satellite or communicating with a drone or anything. So you can apply basically cryptography in many different verticals. But we have been focusing, like I said, in space, drones, and later in the last few months, a bit more in, let's say, so-called defense tech, which is, let's say, derivation of basically what you do with to protect drone communication. And like I say, we reduce the surface attack by using as much as possible hardware, because one of the key factors was also mentioned, you know, is in whatever architecture you build, you need to protect, let's say, the secret key, the private key. Anyway, you need to protect the one cryptographic key at least. You know, of course, you have multiple, and that's a real problem. So if you do, let's say, like we mentioned, or you might have a SIM card where you can store some data, or if you have on a phone, you rely on the operating system, maybe on a database as well if you run on a PC, on a laptop. So you rely on, for example, database. It's a piece of software that stores data. So inherently, you could be attacked, and basically an attacker could get advantage of this and enter and try to steal the key. So at the end, whatever you build, it's very, very important and crucial how you manage to store those keys in a secure way. And that's also our approach in using hardware. So using an encryption chip, let's say in our case an FPGA chip, to store keys inside is definitely more complicated to hack a physical chip than hack a piece of software. And another important bit is, again, you can implement different kind of algorithm and you can implement them in a cryptographic chip. Today, if you go on the market and buy a chip, mostly, you would buy probably American microchip or Chinese or Russian or whatever. So down the line, you can test the cryptography in there. You can have test vector. Let's say you encrypt with that device. You encrypt with some device that you know and trust, and then you can compare and you can say, yes, it behaves, let's say, according to standards. It works, like using AES, ECC, or whatever algorithm. But what you can do is verify that, for example, there are no backdoor in that chip. So you actually, many of the solutions we use today are built based on blind trust. So each of our phone basically has some device, there is a cryptographic chip, and you just trust that there is no backdoor. And there are, of course, many examples has been in the past where some, different kind of integrated chip has backdoor. So and those are, let's say, undocumented, unknown function that, or door virtually, that would allow an attacker to get inside. So using an FPGA has an advantage also in, providing a possibility to basically take a third party and verify all your implementation. If you take an FPGA, you can actually get a third party, read all the source code that actually used to program the FPGA, while if you take a normal chip called ASIC, it's basically like you write the code in a stone, and there is almost impossible that basically a producer and manufacturer will give you the source code of the ASIC or the schematic of the ASIC. It's something usually very well protected. So anyway, it's based on this trust. And overall, like I say, for us it's important to protect data communication for different verticals. And we have done also some work for post-quantum cryptography, because the idea is, of course, to be able to eventually to migrate. So today we use, let's say, what is called traditional cryptography. Mostly we work with the cryptography based on elliptic curve, so so-called ECC. We don't use, for example, RSA at all. I can mention then later also reasons. And then, since we have this chip that we can program, we can then eventually replace the algorithm with, Kyber dilithium from Crystal or any other new algorithm, quantum resistant, that standards bodies will produce. And now, as mentioned, the NIST is coming up with some standard, hopefully by the end of the year, so that your programmable chip can be updated with new functionality and basically migrate to something future-proof. And specifically then, and I will go into those, we have done, I have a couple of examples where we apply this for satellite, and where also we use different kind of encryption algorithm, and I'll come back to this later. So just now to give this, try to understand this main building block. So I say an FPGA chip, so it's a chip that you can program. What does it mean? Basically, imagine to have a Lego bricks, and this square is basically your chip. Inside, you can actually install, you can place a certain algorithm, and you can choose yourself, because you can put whatever you want inside. And those building blocks can be replaced, like I mentioned before. So you could have traditional cryptography and then make a new version, or replacing an algorithm with a quantum resistant implementation. So this is basically the core, so, and the physical, this is a picture of a chip, right? It is exactly the FPGA, one of those that we have been using. And once you have this chip, what you can do is start to build, because with the chip itself, you don't do anything. You put on the table and there is no way to communicate with it. So you need to start to build some more complex circuit called PCB, and which basically means, it's this little board where you have your chip and some interface. So you can connect and do something. For example, was mentioned before, Raspberry Pi. If you have a Raspberry Pi, or if you have any other, even a laptop or computer, then you connect some wire to this little board and you can start to interact. And what you can do basically is communicate with this device, and this device provides you the cryptography functionality. So you can run all the cryptography functionality, generate keys, do signature verification, encryption, anything you want directly inside the chip. And one important thing is that the most important, let's say private key or secret key, they don't leave the chip. So you tell the chip, please, encrypt this, but the key is inside. You can tell the chip, generate a key, store it, let's say, in a slot number 1, and then when you say encrypt, use slot number 1, or when you can sign, use the slot number 2. So you refer to a certain index inside the chip, but you never extract the key from the chip. So everything runs inside there. And now when you have this kind of device, you can build solution. So that's the idea. So this is again your building block, and now you can work how you can use this device for which kind of application. Now if we start to first example for a space application, let's say there is a constellation called Iridium, which is built by tens of satellites which are geostationary, so they run around the Earth, and they give you full coverage, 100% Earth coverage. So you are used to use, for example, GPS or that kind of service, or you rely on certain satellite. Now Iridium give you access everywhere around the Earth, including the poles, which usually is not very, very common. And what you need to connect, you need just a small device. Now that white little box is 4 by 4 centimeter, and behind there is the equivalent is a little square 4 by 4. That's the antenna. It's very similar to the GPS, if you've never seen the small antenna. So with that kind of a small device, which is, you see there the dimension, you can actually connect and send and receive messages. Now Iridium offer so-called short burst data, SBD. So it's a service which is very, very similar to what we're using, maybe not anymore, SMS with a mobile phone. Some years ago we used to send a lot of SMS, and that's exactly the way, a very similar way, how it works, this Iridium service. So you can, with that small device, send this text message, basically around 270 to 340 bytes. Now this device we can actually connect to the little green device I mentioned before, which is our, let's say, encryption building block. So by combining those two, now you're able to ask to the user, and you have an interface with the user, and say, okay, you want to send a certain message, so we can encrypt the message inside this FPGA chip, inside this device, and then we can use the Iridium constellation to send to another end user which has exactly the same device. So you can have two person or two, let's say, endpoints, but in principle 2 users everywhere around the world, and they can basically exchange encrypted, hardware-encrypted messages end-to-end using a very small, mobile device. And one of the application, with this has been specifically, the first one was in defense tech, so you can probably start to imagine, because it gives you the possibility to, people on the ground to send in a highly secure way, basically information, across Earth. And another type of application, very similar, again, using exactly the same setup. Imagine putting this one on a drone. And now the drone, of course, can fly anywhere. It's, drone typically is in the sky, so it has very, very nice view of the clear view, let's say, of the sky. There is no obstruction. So the connectivity actually with any satellite. Satellites, we are talking about something fly around, 500, 600 kilometers. And that's the distance that needs to be covered by the communication device. And then once you have this device on the drone, then what happens? For example, probably I'm sure you heard a lot about this jamming, spoofing and jamming of GPS, in general jamming of radio communication, with nowadays happen very, very, constantly, for example, in Ukraine. So what you do when you talk about jamming, that means when you communicate among devices, you use a radio. The same way I'm talking to you. Let's make this. I'm talking to you, and you listen to me probably without any issue, even on the last row. Now imagine there is someone with a power amplifier playing music next to me. So the guy probably in the first line, maybe if I scream a bit, so if I use enough power, will be able to listen. But the guy in the last row, probably even if I start to scream, they will not be able to listen. This is exactly what jamming does and how it can be done. So you take just a powerful transmitter and you send almost like music or random noise on a very different frequency. So you try to kind of, obliterate anyone else try to talk. And this is exactly what is the way it works jamming. This is exactly the way it works, for example, nowadays in Ukraine. So you have, a lot of drones flying, and you have opponents try to jam them so that you cannot control them anymore. And one of the possibilities, for example, is to, imagine I'm talking to you and then I'm a drone. And if I'm talking to you of this distance, again, I have jamming that try to block my communication. Now, if I have a different device, which is, for example, this one, talking up to the sky on a very different frequency, then it becomes, let's say, more complicated to try to jam with the same device, a communication that actually goes up, and the drone is already up in the sky. So it becomes a little bit, not impossible, but definitely, let's say, more resilient to this, to different kind of jamming. And this way, the drone basically is able still to communicate with the base and is able to fly and be recovered and not, shot down or captured. So that's a very practical example of this kind of connectivity thanks to the Iridium. And another one now for we change completely, let's say, subject. Now, with my company, we had one of the last contract with the European Space Agency. It was called FISON, which acronym was for Your Eyes Only. And this is just let's say, a demonstration in space of this, let's say, our technology, so the development we have done for this FPGA chip. We wanted to demonstrate how it works basically from space. So having, let's say, protecting communication from a satellite to the ground. Now, there should be, okay, video coming. Is it? Yeah, next one. So motivation, again, we wanted to demonstrate in space this kind of technology. I can tell you in space, when you start to use, the standard of space, let's say, data communication, it's unfortunately very, very, let's say, now you can call it almost prehistoric environment. So the standards are very old, and which means that cryptographic or encryption algorithms they use are very, let's say, old. So they don't talk at all. I mean, at the moment, there is nothing related to quantum cryptography, post-quantum cryptography. There is even no standard talking about public cryptography. So there is no concept of digital signature and digital certificate in the current standards. And I'm talking about, CCSDS kind of stuff, so the worldwide organization that, combine NASA, ASI, all the major space agency. So this kind of catch-up job, it's absolutely very slow. So, and that's why there have been probably in the last few years a lot of talk and hype, because in principle many satellites are very, very, I would say, easy to hack. They are not very well protected. And what happened today in any basically company that try to do some business with space is that everyone try a bit to improvise, find their own solution, because there is no standard. So you don't have a standard that you can follow and say you have some best practice, but in space there is basically nothing. So every company try to do his own cooking recipe, and many times when you try to talk to them, of course no one wants to tell you exactly how they do, because they're probably afraid of admitting some issues or some weaknesses. So unfortunately this is really the current situation that you face. So this is one of the reasons why we wanted, if you work with cryptography, and at the end it's let's say doable, you can make an implementation and follow exactly what we do on Earth. Internet is full of, PKI I use daily, so this kind of technology used since many, many years. So there are, very well-defined standards and very well-defined way of how to do the things properly. So in my mind, when I started to work on this, I thought, okay, it shouldn't be rocket science to use exactly the same approach and use in space, because at the end, what is the difference? There is just 500 kilometers, wireless connectivity, and that's it. The rest is cryptography should be exactly the same. So although we are a small company, so we say, okay, let's try to demonstrate it actually it's possible. So we had this hardware security module, so our FPGA, we say let's put it on a satellite, and lucky enough, ESA had a satellite called OWASP that had, because actually fell like I think a month ago, so it was in orbit for about 4 years. It's actually render is very, very realistic, let's say. So it's a so-called CubeSat with three units. So it's 10 by 10 centimeter and it's 30 centimeter long. So it's an object like this, which has been launched and managed by ESA for a number of years, has been in orbit actually for 4 or 5 years, which is quite astonishing. I mean, it's quite long for that kind of device. And then slowly, you launch a satellite. Actually, I don't know if you are aware, but you have this, rocket, and then opens, let's say, the mouth, and the satellite's literally released with a spring, mechanical spring, at a certain height, and that's it. You just launch this. Of course, there is a very high velocity of the vector. Let's say the rocket that was bringing the satellite, and then the satellite will just rotate around the Earth, and slowly, because at that height anyway there are some particles, so it will slowly lose its kinetic energy and slowly will eventually be attracted more and more by the Earth and will fall on Earth, or actually will burn in the atmosphere. This is the way all the CubeSat and mostly this small nanosat works. So they don't have any engine. So you just launch them and then you wait that they fall back. So the OWASP, lucky for us, has actually also an FPGA on board. So that means the kind of chip that we use. We don't care about the brand of the FPGA. We can use an FPGA. So the idea was like, okay, the OWASP has an FPGA. Let's reprogram it remotely. So we install our cryptography functionality. Then let's install some software and let's demonstrate some cryptography. Now, there should be this video which Stefano, I think, had to switch. He told me to go. Let's see if we find Finder. There it is. Magic happened.
There is volume? You need volume?
Yes. Okay, doesn't start. So you can put volume and...
You want volume?
Yes, possibly, yes. Yeah, actually, yes, because it's 1 minute, very, very...
The following video is an explanatory video of our in-orbit demonstration on the OWASP satellite. The satellite is already orbiting around Earth. The receiving station is at ESA ESOC in Germany. Here they will receive all data which will travel via internet to Tallinn in Estonia. At our Scudo headquarters, we receive the data to be decrypted. Let's go back to space and let's dive into what happens inside the satellite. Our focus has been on reprogramming the onboard FPGA chip. A RISC-V processor marks the clouds in yellow, while an HSM encrypts both images. The satellite sends the encrypted data to Germany, and from there we receive it at our office. Here, everything is decrypted using the designated digital certificate, which concludes the demonstration. Thank you for listening.
So this was, okay, I will do...
Chrome.
Sorry?
Chrome. Google Chrome. Yeah.
Google Chrome. Back, sorry. You see, I'm not a Mac user. Okay, so that was very, very simple, but now I'll go and dive it a little bit more. So we have this experiment, the code, this is the ESA code 251, which is on the satellite as dual, let's say, approach. So on one side, we wanted to demonstrate the cryptography part running on the FPGA chip. And at the same time, we wanted to demonstrate the so-called edge computing. So having a RISC-V processor basically is a way for running any kind of program, let's say C language. Yeah, of course. And running any kind of program. So RISC-V, if you're not familiar, it's like a processor basically. So you can run C language or any, well, in principle C language is the easiest for the RISC-V. So inside the same FPGA chip, you have one area dedicated to cryptography, which run the same way I described before, and then you have an area where you can run any kind of software, and you are within the border of the cryptographic chip, let's say the FPGA. So you have inherently this extra security of being inside a physical chip, rather than having a program running on a CPU, operating system, database, and all sort of stuff. So again, in the idea to combine, I have a little bit more security. So we reprogrammed those, and that means the project was to collect picture from the satellite. The satellite has different payload, different sensors. So there was a camera. We snap a picture, then we send this data inside the FPGA, which we reprogram from ground. So let's say the FPGA on the satellite was running our code and our programs. So the simple picture of Earth you will see later, but basically, as you know, you have Earth, you have probably sometimes you have clouds, white clouds. So all we've done very simply, we say, okay, let's find the clouds. So we run in the RISC-V processor some image processing functionality to mark the cloud that they're white, let's mark them in yellow. And again, it's very, I would say, stupid kind of example, but it was just an idea to show, what could be done. Of course, you can do way more complex application, but just elaborate some image, and then you have these two images. You have the original one, which I call the white clouds, and you have the processed one, which is the yellow one. And then we could actually encrypt, and again here using digital certificates, so asymmetric cryptography and symmetric cryptography. I'll come back to this. We wanted to encrypt so that one picture uses a certain key, so a certain digital certificate, and another picture a different one. So all the basic idea was that on the ground we were able to say, okay, a certain user with the right key, let's say number 1, can decrypt the picture, maybe the white cloud picture, and the other user with the key number 2 anyway, another different key, can decrypt and access the process picture. So this was, again, it's a very simple example, but in space, since there is nothing demonstrating or no standard that providing asymmetric cryptography, was a very easy way to demonstrate that actually you can collect data on a satellite, encrypt with specific key belonging to specific user on the ground, and then when you send the data, even if the data go through a satellite, a ground station owned by ESA, different kind of station in the middle, but they are still encrypted end-to-end, and only the end user, for whom the data are designated, is able to decrypt it, because he has the right, basically, private key or the right device in our case, because we use an FPGA chip, so he has the right FPGA chip to decrypt the data. And just to let you know, because again, for us or for the people that are working with this kind of technology, it's very kind of simple, but just to imagine, there was a mission, and I can tell you even why I end up with this, doing this demonstration. There was a mission a few years back, probably some of you remember, now I don't remember anymore the name, but anyway, there was a NASA involved, and there was a company in Italy that built a satellite, and then they launched this satellite and they hit a comet. So all the idea was to try to hit this comet and then record, let's say, the last seconds between impact and during the impact, let's say. So it was a very nice, of course you can imagine, a very nice scientific experiment, which was very successful. And then I was talking with the guy responsible for building this part and collecting the information. So they were, and it's a public information, there was a webinar actually, I was listening, and then I talked to the guy. So the guy said, well, NASA told us we have to collect this picture. There were about 600 pictures. And then NASA told us no one must be allowed to watch this picture. So you will download the picture to your office, wherever it goes through, whatever antenna. Then you pack them, so there must be one guy locked in one room that will receive those pictures. Then you pack them, he didn't say, but I could imagine encrypting or something, and you send it to us, NASA, in US. And then they will release publicly whatever picture they want. The main point was that there was, of course, some, let's say, device on the satellite or wherever that they didn't want to show publicly. So they say, we need to make sure that we show whatever we want. But they already, in there, just make me think. So, and this was happened a couple of years ago. So, because there was, no usage of simple asymmetric cryptography, they had to come up with something like this. And that's why I say, okay, let's demonstrate that actually it's doable. That's why I've done, just two simple pictures with two different keys. And the setup now is very interesting. When this is now working with ESA, so they had this satellite. Then they have the so-called flatsat, which is, let's say, a replica of the satellite, which you see on this left picture. This is in Darmstadt. So it's the real hardware of a replica of the satellite that is orbiting. Because every time you want to, let's say, put your software in space, for example, in this case, in this satellite, you want to ensure that you don't make any damage. So they need to run your software in a quite complex way, in many ways, just to ensure that it behaves properly and doesn't damage anything around. So the easiest way, of course, is to have a replica, at least, of the electronics, the computational part on the ground, and then you run it in there. So we had to go through this flatsat system. Plus, to make it even a bit easier, we replicated the flatsat of ESA. So on the right side is the picture from our office, because at the end, when you do and implement these things, especially let's say in using hardware, there are always differences, and it's not always that simple. So rather than working remotely with some place in ESA and try to test remotely if our software works, then we thought, and it was a great decision, we thought, okay, let's buy exactly the chip that is running that satellite. So that little board that you see, this flat wire arriving in the middle, basically that little board is exactly the same model and brand which was on the OPSAT. And by the way, when I started to discuss about this project and I understood that we would work with that device, I went and buy online this board, and it was the last one available on the online shop. So I was like, even before starting the contract, I was like, okay, let's get it, you never know. And afterwards, I think I was very happy that we have done. Anyway, so the setup, it's, I would say, quite complex under a certain way. There is a lot of software that we got from ESA. So try to replicate whatever runs on the satellite. Satellite has been designed and launched many years ago. So at the time, for example, for whoever is familiar, there was this Angstrom operating system. It's let's say, version derived by some sort of Linux, but it's like outdated completely. There's almost no support, and very complicated to even compile anything. There is even no compiler on that distribution. So anyway, overall the setup was very complex to start to implement even the most simple thing. And of course we wanted to keep things simple, but we had to face this, these challenges. This is just, don't get scared, but anyway, just a picture of the inside of the FPGA. Unfortunately, with this resolution, you can't basically read anything. Those are the building blocks that more or less you saw in the first picture, the yellow picture. So they are different, on the right side, actually, there were different cryptographic functionality. Then there are basically, on the left side, there is the ARM, so it's another CPU that runs on the satellite, which runs its own Linux. And so we had to communicate between our implementation in the FPGA and the external computer, because remember, we had to capture picture, so we had a software talking with the satellite, capturing picture, and then this data needs to go inside, reach the cryptographic functionality. So we had to build different kind of interfaces. Now there's some name for those that are familiar. I don't want to bother you with too many details. And but this basically was the hardware setup we have to face in there. So now coming to the cryptographic part. So the demonstration here was, like I say, we wanted to demonstrate the use of asymmetric cryptography. For those that don't know, in a simple terms, that basically means having two kind of keys. They are always going in pair. One is a private key and one is the public. Just imagine, so the public key is the one you can give to anyone, And the private key is exactly the one that you need to hold, very dear and never reveal to anyone. Like, we heard also before, is the one you use, for example, to sign any document. So it's you need to keep it very well protected. So we wanted to demonstrate this asymmetric cryptography, and one very well known and established architecture is called this ECIES. So that's combined this asymmetric cryptography with the symmetric cryptography, simply using, for example, an algorithm called AES that we talked before. So this means you have these two endpoints. So one was our office and one was the satellite. In both, we have this chip, this FPGA chip, right? So in our office with our own, in the satellite, we used whatever was available. Now, these two chips, what they do, and I make it very, very simple, they generate itself this key pair, so private and public. So inside the two chips, you have the private and the public key. Then what you do, you exchange the public, because the public can be easily exchanged. Now we can go into the way of protecting, but let's assume for simplicity, you just exchange the public key. Then you can run an algorithm which was mentioned before, is Diffie-Hellman. So you run some, let's say, magic, but anyway, it's an algorithm where on one end, using your private key and the public key of the other guy, and on the satellite do the other way around, he's using his own private key and my public key from the ground. You run this algorithm, and this generates the so-called secret shared key. So basically, it generates a third key, which is the same. So every end has used the same key, but it's not exchanged, because we didn't exchange that key, we exchanged the public key. This is the beauty of this algorithm called Diffie-Hellman. And from there on, you can derive let's say, new or different cryptographic key, and those are the one you can use to encrypt your picture. So in our case, since we wanted to do two different user and two different let's say, digital certificates, so we generate multiple key pair, in this case at least two. And that was just the basic idea to apply to then the image. So, okay, and we did the demonstration, actually was 18th of October, okay, last year in the FlatSat, because first you have to do the, show to ESA that actually all your software runs smoothly without damaging anything. And it's a very thorough process, which, by the way, very interesting to run. And then in the 3rd of October, and fun enough, we have two dates, 30th of October and 9th of November, because the way it works is that once you test in a FlatSat, you basically give to ESA all your software packaged in a certain way. They load in that replica of the satellite, they do all these tests themselves, and then they tell you, you passed the test. Now, they have your software, so they are responsible now to take this software and bring it to the satellite, and then they run the experiment. So you basically are sitting in your office and waiting that they send you the output, so the file that we were encrypting. And fun enough, this was 30th of October, they were telling us, didn't work, and then they send us all the output file. Then we were watching this log file, and we say, this is really, we couldn't understand. And we told them, well, you load the wrong software. I mean, this is not our software. You're running someone else. And of course, it's a little bit awkward because, I would say, how they could make this kind of, and then, no, it's impossible. I tell you, listen, it's really like, we have the log file. I mean, I can show you, and then we show you, and then eventually, they didn't explain why, but they say, yes, they admitted they had some issue. So we have to redo it. And then we're like, okay, very good. So they rerun on the 9th of October, and I think there was a conference, this software-defined space conference here in Tallinn, where I was supposed to present the results. And I think it was exactly the 10th of November, maybe, because I remember I received the files in the night before the presentation. When I arrived in the morning to give the speech, and these are actual pictures from the satellite, by the way. Those are the original one. So I got them in the night, so I managed to, copy paste to the slide just during the morning. And this is just resembling like the path I was telling you. So now, okay, it is very small, but basically it's a Earth picture with some clouds marked in yellow, encrypted and processed, and then using two different keys, we have been able to demonstrate that, of course, the right key is able to decrypt only one file. So we also as a proof, we also exchanged and demonstrated that it wouldn't work the other way around. So that means you can, like I mentioned before, so you can define and decide that whoever user you want with the right digital certificate, because behind there is a digital certificate, you can actually encrypt one data, whatever it is, and ensure that only that person with the right digital certificate can decrypt it. So at the end was very successful for us also very rewarding, because at the end we had space demonstration of this technology, and then so now we are continuing to work in that direction and still working with space and drones. Thank you very much. Hopefully it was not too boring. If you have any question, I see here. Okay, let's start